Hello everyone. Let's start with a thought. Why do satellites need so much fuel to reach orbit? And then, strangely, they seem to float effortlessly? The secret is in their energy balance. An orbiting satellite has kinetic energy because it's zipping around Earth and potential energy because Earth's gravity keeps pulling it inward. The sum of these two, kinetic plus potential, is the satellite's total mechanical energy. And believe me, this total tells us everything about whether the satellite stays bound to Earth or drifts off into space. Let's first talk about the kinetic side of the story. For a satellite of mass m, kinetic energy is 1/2 mv squared. But we know the orbital velocity is square root of gme divided by re plus h. Substitute that in, and kinetic energy comes out as gmem divided by 2 times open bracket re plus h close bracket. Here's a fun way to think of it. Satellites closer to Earth are like cars speeding in the fast lane. They need more kinetic energy to stay balanced. Farther away, the orbital speed is lower and kinetic energy drops. That's why high-orbit satellites cruise gently compared to low-orbit speed demons. Now let's flip the coin and talk about potential energy. At a distance re plus h, the gravitational potential energy is minus gmem divided by re plus h. The negative sign is a reminder the satellite is trapped in Earth's gravitational well. And here's the neat balance: the magnitude of potential energy is always twice that of kinetic energy. So potential energy acts like the heavy anchor pulling the satellite in, while kinetic energy is like the engine keeping it moving forward. Together, they create the delicate dance of orbital motion. Now, let's put the two together. Total energy equals kinetic plus potential. Substituting the values, we get minus gmem divided by 2 times open bracket re plus h close bracket. This result is huge. The total energy of any orbiting satellite is always negative. That's the cosmic seal of a bound system. If, somehow, you pump in enough energy to make this total zero or positive, the satellite is no longer bound. It will escape Earth's grip forever. That's exactly what happens when we calculate escape velocity.
But wait, not all satellites move in perfect circles. Many have elliptical orbits. In this case, the energies keep shifting. At perigee, the closest point, the satellite is racing. Kinetic energy is at its maximum. At apogee, the farthest point, it slows down. Kinetic energy is minimum. Potential energy plays the opposite game. It's most negative at perigee, less negative at apogee. Yet when you add them together, the total energy stays constant and negative throughout the journey. That's physics keeping its books balanced, no matter what.
Now let's crunch some numbers with a real example. Suppose a satellite of 400 kilograms is moved from an orbit of radius 2re to one of radius 4re. The initial total energy is minus gmem divided by 4re. The final total energy is minus gmem divided by 8re. The change in energy comes out to about plus 3.13 times 10 to the power 9 joules. That's billions of joules. Most of this energy goes into increasing potential energy, even though the satellite's kinetic energy actually decreases. So when rockets burn massive amounts of fuel to raise satellites to higher orbits, they're mostly paying the potential energy bill. Let's wrap it up. For a satellite in circular orbit, kinetic energy equals half the magnitude of potential energy. The total energy is negative, minus gmem divided by 2 times open bracket re plus h close bracket. This negative energy keeps the satellite bound to Earth. To change its orbit, we must supply energy, mostly to lift it higher against gravity. That's why launching and maneuvering satellites isn't just about speed, it's about carefully managing energy between motion and gravity. So the next time you hear about a new satellite being placed into orbit, remember, behind that headline is a clever energy balance, billions of joules of fuel, and the timeless laws of Newton and gravitation at work. See you in the next session with yet another thrilling journey into the physics of the universe.